Today I'm away from my whiteboard because I'm going to use some animations to explain how DC motors work. This is a schematic diagram of a permanent magnet DC motor. We have the permanent magnets, which are these blocks here and here, with the north poles to the left and the south poles to the right. These are mounted on the frame of the motor and don't move, so that whole assembly is called the stator. Then we have the armature, which is coils of wire wrapped around laminated soft iron, and they are on a shaft so that the whole armature can rotate, and so the armature is also sometimes called the rotor. In the middle of the armature, on the armature shaft, is the commutator. This is a split ring of copper that is used to make contact with the coils of the armature. And these black squares are the brushes, which are graphite blocks that make contact with the commutator and take electricity to it. And then we have the wires going back to the battery. Now, remember that whenever you have electric current flowing, you have a magnetic field around the wire where the current is flowing. And if we wrap that wire in a coil, that causes the magnetic field to be concentrated and also puts the poles of the magnet along the axis of the winding. So if we follow the current through this armature, start at the battery, the conventional current goes across the top to the top brush, connects to the left side of the commutator and then to the left side of the armature winding. The current is generally going from the lower right to the upper left, so we start at the left side of the armature and the current is going from the middle to the end. And with the direction the current is flowing and the direction these windings are wound, we end up with the north pole of our magnet on the left side of the armature. And of course the south pole would be at the right side, but we'll take a quick look at that in a moment. So the current goes from right to left. The current then travels over to the right side of the armature, and notice that the current comes back into the armature, still going from right to left. So on the left side it goes from the middle to the outside, goes over to the right side, then goes from the outside to the middle, so the current is going the same direction. The coils are wound the same way, so we get the same orientation of our magnetic field. So the whole armature has the north pole to the left and the south pole to the right. So we see that the orientation we have here, we have a north pole of the armature near the south pole of the left permanent magnet, and the south pole of the armature near the north pole of the right permanent magnet, and they want to attract each other, and the armature wants to line up with those permanent magnets. So there is a rotational force wanting to make this armature rotate counterclockwise. As it rotates, momentum is going to carry it past the middle, and so look what happened as it passed. Now the brushes are contacting the opposite sides of the commutator. So now the current is going out from the middle on the right side and from the outside to the middle on the left side. If we back up again, we see that before we had the current was going generally from right to left. After we pass the magnets and the commutator switches which side is connected to which brush, now we have the current flowing the opposite way. So now the north pole is to the right and the south pole is to the left, and we see now that the left side of the armature is going to have a south pole that's going to be repelled by the south pole of the left permanent magnet. That's going to make the armature want to continue rotating counterclockwise, and of course on the right side we see that the north pole is now on the right and is being repelled by the north pole of the right permanent magnet, making it want to continue rotating counterclockwise. And as it rotates, as it passes the vertical, now we are coming closer to the north poles and the south poles lining up again. So now we are right where we were before. We see that we have the north pole on the left and the south pole on the right. The left side of the armature is attracted to the south pole of the left permanent magnet. The right side of the armature is attracted to the north pole of the right permanent magnet, and they want to line up. And once again, momentum carries it right past. We get the switching at the commutator, which switches the polarity of the armature. And it will just continue doing this ad infinitum and go round and round as long as we have the battery hooked up this way on the motor. Now if we flip the battery over, what happens? We see here now that we flip the battery and the north and south pole flipped, so now the armature wants to rotate clockwise instead of counterclockwise. So if we put the battery on one way, the armature rotates one way, And if we put the battery on the opposite way, the motor wants to rotate the opposite way. So with a permanent magnet DC motor, we can change the direction that the armature rotates by changing the polarity of the voltage hooked up to it. Now this diagram shows a two-pole permanent magnet DC motor, and there's a serious problem with it. They do make them, I have seen them, but they do have a serious problem, so they're a little bit rare, and let's take a look at what that problem is. Let's say that you cut the power and the motor coasts to a stop and the armature comes to rest perfectly aligned with the permanent magnets. Look at the commutator. We now see that each brush is connected to both ends of the commutator. If we look at the left side of the commutator, we see that it's contacting both brushes. If we look at the right side of the commutator, we see it's contacting both brushes. So basically both brushes, and thus the battery, are just shorted across. The current just goes from one brush through the commutator to the other, and no electricity goes through the armature. So if a two-pole DC motor comes to rest with the armature perfectly aligned with the magnets, which can happen fairly frequently, we don't get any power to the armature, and so we hook up the battery and it's not going to start up. It's just not going to move. I had a little toy car when I was a kid with a wired remote control that you press the button, the car would go, and sometimes it just wouldn't go unless you gave it a little push. And when I got a little older and learned a little bit about electricity, I took that apart and I discovered why. It had a two-pole DC motor in it, and whenever that motor came to rest, perfectly aligned with the magnets, it would not start unless you gave it a little push. So you don't see two-pole DC motors very often. Usually you see three-pole DC motors, which is what we have in this diagram here. So here is a diagram of a DC motor with a three-pole armature. If we follow the current, you'll see that in this particular position, I rotated it around so we can see the connections best. We see we're connected to the upper left side of the commutator, which goes to the left side of the armature. The current is going the same direction as with the two-pole armature, comes back to the middle and back to the lower left side of the commutator and back to the battery. So we have our full power going to the left side of the armature. The other two poles of the armature, notice that we connect to the top side of the commutator. We go up the upper right side of the armature, and then notice there's no connection to the upper right side of the commutator. So the current continues down to the end of the next pole of the armature and then back to the middle. So we actually have a path of current that goes through twice as much wire in the other two sides of the armature. So there's half the current flowing through there, twice the wire, twice the resistance, half the current. But we have twice as many coils of wire, so that compensates, so we have just as strong a magnetic field. And so we have two south poles on the ends of this armature. I've colored these gray to indicate that the magnetic field is only half the strength, but we have twice the armature coils, so we actually have the full strength magnetic field, and because of the orientation, that south pole is halfway between those two poles of the armature. So the magnetic poles of our armature are aligned up pretty much the same way as with the two-pole armature. So we have a north pole here and a south pole right about here, almost lined up with these magnets. They want to line up and stay lined up, and so the armature is going to want to turn counterclockwise, but just like before, as the momentum takes it past, we switch which part of the commutator is connected to which brush, and notice that we now have our connection going such that we get our full power to the lower right side, and the direction of the current is such that it's going from lower right to upper left. So our north pole will be to the upper left, south pole to the lower right. So there's a south pole right here, attracting us to the north pole of the right permanent magnet. And now if you follow the current, you'll see that it's going through both coils on the left side, giving us half the current, but twice the turn, so we have the same magnetic field, and because of their orientation, that magnetic field is centered up about here. And so now we have our north and south poles aligned like this. This north pole is attracted to this south pole. This south pole is attracted to that north pole and wants to keep the armature rotating. And as it rotates and as it passes by, the contacts change, and we get a constant changing of our magnetic field, and we get the same rotation with our three-pole armature as we do with the two-pole armature, but there's no position where the armature will not turn when we hook up power to it. Now, your typical small DC motors will have three-pole armatures. But as they get bigger, we start adding more and more poles. So this is a diagram of how we get started, but we're going to get more and more poles as that motor gets bigger. But your typical small DC motor will have a 3-pole armature. We know that when you pass an electric current through a wire, you get a magnetic field around that wire. We also know that when you pass a wire through a magnetic field, that as long as the wire is moving, that we get an electric current in that wire. So what I've done here is I've redrawn the motor armature. I've made it more compact. This is actually a more realistic configuration. I had it stretched out before because I think that helps us visualize how the armature would line up with the magnetic fields of the permanent magnets. But I don't think that's going to work for what I'm going to demonstrate now. So I've made the armature more compact, and I've made the permanent magnets taller so that the armature stays within the main part of that magnetic field. I've also eliminated the commutator. Notice that I have what are called slip rings now. So instead of a commutator with splits that has that switching action, I now have rings such that one side of the armature is always connected to one brush and the other side of the armature is always connected to the other brush as the armature rotates. And over to the right, I've removed the battery and I've put an electric meter here instead, because what we're going to see here is how a motor can act as a generator. Now look at the way the armature is wound. The wires that we see going across our vision or up and down are never going to rotate through the magnetic field in such a way that it'll create a great deal of electric current. But the wires at the top up here are wound away from our vision, so they're going away from our eyes, and down at the bottom they're coming toward us. And those wires are oriented in such a way that when they're moving in this direction, they're moving along the magnetic field and they're not producing much current. So look at the meter over at the right, and the needle is straight up and down indicating 0 volts. So the meter shows us positive voltage to the right and negative voltage to the left, and straight up and down is 0. So as the armature is moving in this area, we only produce a small amount of current. But let's let it plunge on down and rotate 90 degrees here. Now the wires are moving across the magnetic field and creating the greatest current in the wires. So you see that the needle has gone all the way to the left, so we're creating our greatest negative current at this point. And as it continues rotating, the wires come around and they're now going along the magnetic field and producing the least amount of current, and it goes up to 0 volts. But as it continues rotating, now the wires are going the opposite way through the magnetic field, and we get our greatest positive voltage as it rotates around. And then as it comes around to rotate across the field again, our current goes down to 0. And then this repeats as we rotate around, the left side going down, the right side going up. We get our maximum negative voltage or maximum negative current. And then as it rotates around again, we get our maximum positive current as the armature rotates this way. I showed this without a commutator now because I think it better illustrates what's going on. Because as the armature rotates through one half of its cycle, we get current flowing one way, and as the armature rotates through the other half of its cycle, we get current the other way. And I think that makes a lot more sense to illustrate this that way right now. But of course now we're talking about alternating current. A lot of places will say that this is how alternating current generators or alternators work. That's really not quite true, because alternators are usually not constructed this way. This would work, but a practical alternator is actually constructed differently, and we'll talk about those when we get into alternating current. But the main difference is that usually we have the coils that produce the electricity not moving, and we have a magnet rotating around inside the coil. So we kind of reverse that. Instead of stationary magnetic fields with the coils rotating through the stationary field, we usually have a stationary coils with a magnet rotating around inside them. So it's kind of backwards from what I'm showing here. And also alternators tend to be 3-phase alternators, which I really don't want to get into at this point. We'll learn about that in alternating current. So this is a basic schematic of an alternating current generator, showing once again that as it rotates one half of its cycle, we get current flowing one way, and as it rotates through the other half of its cycle, we get current flowing the other way. So now we have basically the same idea, but now I've put the commutator back. So I've made this into a motor again. This will work just like the other one, except it's more compact and a more realistic configuration. And now we have the commutator again. And now as the armature rotates through this part, we get 0 volts as we did before, but as it rotates through this side, we get our maximum current. We're getting our positive current over to the right as you look at the meter. And as it comes down around where we get our lowest current, it goes to 0 volts in the meter, but notice that the commutator switches which side of the armature is connected to which brush. And so when it rotates the other half cycle, we get positive voltage again. So we get the current trying to flow opposite directions, but the commutator switches it over so that it always flows the same direction. And so we've taken a DC motor, and what we've done is taken the battery off, and instead of the battery giving us current that gives us magnetic fields that make the motor spin, now we spin the motor mechanically. In fact, here's an example right here. I have the small motor hooked up to an analog meter, and as I spin the motor, you can see the needle move, and it only moves one direction because even though the armature is going through the magnetic field one way and then the other way, the commutator keeps the current going the same direction, and so the needle only moves one direction. But if I move the motor the opposite direction, the needle moves the opposite direction. So a motor acts like a motor. You hook up a battery to it and it rotates, but if you take the battery off and put a meter there, we can rotate it and see that it creates current. And so this is how a generator works. So now we see that we can make the motor act as a generator. So let's take a quick look back at our permanent magnet DC motor and watch it go around a cycle or so. Just to remind us how it works, we have the magnetic fields created by the field magnets and the armature rotating, and the commutator switching which side of the armature is connected to the battery so that it continues its rotation like we already described. So this motor is made with permanent magnets. Could we not use electromagnets for those magnets? Yes, we could. So instead of having heavy permanent magnets, we can make this same motor with much lighter weight electromagnets. And here that is. So notice in this particular motor, we have the electromagnets are simply wound in series with the armature. Notice we come from the battery, from the positive, over to the left electromagnet, and I've labeled this with red and black not to show positive and negative, but to show the north and south pole. So north on the left, south on the right, just like we had before with the permanent magnets. And that goes through the armature, so the electricity just keeps on going through the armature just like it did before. And then when it comes off the armature, before it gets back to the battery, it goes through the other field coil, and once again labeled red and black to represent the north and south poles. And if we watch this go around, we'll see it works exactly like the permanent magnet DC motor did before. The commutator switches at the right places. The current does not change direction through the field coil, so the magnetic fields stay the same there, and it simply operates the same as the permanent magnet DC motor, except that it's made with electromagnets. But let's see what happens if we reverse the battery. So there we've reversed the battery, and we see that when we look at the field coils, as we expect, the current is going the opposite direction through the field coil, so we get the north pole on the right and the south pole on the left, just the opposite. But it also reverses the magnetic fields of the armature. So we reversed the polarity of the field magnets, but we also reversed the polarity of the armature, so consequently it's going to rotate the same direction. So with a permanent magnet motor, if you flip the polarity of the battery, the motor runs the opposite direction. But with an electromagnet DC motor, if you flip the polarity of the battery, the motor still runs in the same direction. So with this arrangement here, no matter which way you put the battery, either this way or this way, the motor is going to turn counterclockwise. So the only way to get the motor to reverse direction is to reverse the polarity of the current through either the field magnets or the armature, but not both. So here we've reversed the polarity of the connections on the field coils, and that reverses the polarity of the field magnets, and that causes the armature to rotate the opposite direction. I could have gotten the same effect by leaving the polarity of the field magnets the same and reversing the polarity on the commutator, which is basically what we do when we reverse the battery on the permanent magnet motor. So with an electromagnet motor, it works the same, except to reverse the direction the motor turns, we can't simply reverse the polarity of the battery or other DC supply running the motor. We have to reverse the polarity of either the field magnets or the armature, but not both. So an interesting thing about the electromagnet DC motor is they can be optimized in such a way that they'll work on alternating current or direct current. Here is a electromagnetic DC motor hooked up to alternating current. If you look over to the right, you see instead of a battery, I have a source that's constantly changing polarity. And as it does, all of the magnetic fields change polarity, and so the motor continues to rotate in the same direction. Now, it's not quite so simple. For this to work well, it has to be optimized to work this way. If you take an electromagnetic DC motor that's optimized to work on DC, it will probably work on AC, but very inefficiently. But they can be optimized in such a way that they will also work on AC. And that's what you get in your typical electric drill motor and a lot of appliance motors. They are actually just simply DC electromagnet motors that are optimized to work on AC, so they are basically universal motors. And so as we see this go, and as the polarity of the voltage continually changes, we see that the motor continues to turn in the same direction. Now, if we put alternating current to a permanent magnet motor like I have here, the armature will just continually try to rotate one way, then the other way, then one way, then the other way, and it won't go anywhere. It'll just go back and forth. It'll just vibrate. But once again, we hook up that AC to a electromagnet motor, and it'll work just fine. Doesn't mind the polarity changing at all. And of course, to reverse the direction, we have to reverse the wiring to either the field coils or the armature, but not both. And that would reverse the direction the motor goes. So your electric drill motors and many appliance motors, even though they are actually running on AC, the motor design is the same as an electromagnet DC motor. In reality, the armature probably moves faster than the switching of the magnetic field. I show the magnetic field switching faster than the turning of the armature. Usually the armature turns faster than the magnetic field changes, but that doesn't really matter. That's just a little harder to illustrate that. So the magnetic field is constantly switching as the polarity keeps switching, but the motor just keeps running in the same direction. Another thing we can do with the electromagnet motors is we can wind them differently. Again, this is series wound, which means that the armature and the field windings are in series with each other, but we could also put them in parallel. So here we have the field coils wound in series with the armature, but here we have the field coils wound in parallel. When the field coils are connected in series with the armature, we have what's called a series wound motor. But when we connect the field coils in parallel with the armature, we have a shunt wound motor. A shunt meaning a bypass or something going parallel. Before I talk about the differences between a shunt wound motor and a series wound motor, I need to go back to talk about a generator. If we put current into a motor, the motor turns. But if we turn the motor, then it creates electricity. So the motor acts like a generator if we turn it. So when we put electricity into a motor and it turns, is it not also generating electricity? And the answer is yes, it is. And the current that it's generating pushes against the current that's coming into the armature. So the armature is turning because we put electricity into it, but at the same time it's generating electricity that pushes back against that current. This is not quite the same as a simple inductor. When we push current into an inductor, it builds a magnetic field. That magnetic field crosses the turns in the inductor and generates a current that opposes the current that's causing the magnetic field. So when we first start to put current into an inductor, it opposes that current flow. But as the magnetic field slows down and stops getting bigger, then it no longer opposes the current flow, and current flows freely through the inductor. And then, of course, if we try to stop the current, that magnetic field collapses, and the collapsing magnetic field tries to keep the current going. In the case of a motor, as long as the armature is turning, it's going to be producing this current that opposes the current that's making it turn. And this is called back EMF. EMF means electromotive force, so we're talking about voltage, but we have to have voltage pushing that current. So we have a voltage that pushes the current, and it's referred to as back EMF. And so when the armature is turning, whether it's being turned by external means or being turned because of power hooked up to it, it's producing back EMF. The slower it turns, the less back EMF it produces. And the faster it turns, the more back EMF it produces. So when the armature is turning slowly, it has more current flowing through it and a stronger magnetic field. And when the armature is turning fast, it has more back EMF, less current flows through it, and it has a weaker magnetic field. Now, in the case of a series wound motor, where we have the current that runs the field coils also going through the armature, as the armature slows down, it produces less back EMF. In other words, more current goes through the armature as the motor slows down. And so let's say we have a high load on it. Well, let's say you have an electric drill and you're drilling through some hard material and it starts slowing down the motor. It's going to get less back EMF, so more current will flow through it. More current flows through the armature as well as the field coils because they're in series. Remember, in a series circuit, we have the current the same everywhere. So as the motor slows down, we get more current. More current gives us more magnetic field for both the armature and the field coils. So as the motor slows down, we actually get more torque out of it. It actually has more force wanting it to turn. So series wound electromagnetic motors are used in conditions where you want good high starting torque, such as electric drills or starter motors, or any place you want a good high starting torque. A series wound motor should never be started without any load on it. So you must have something holding it back. In your typical electric drill, the gearing that runs the drill itself and usually the fan in there that's used for cooling is enough load to be safe. But without any load, it starts with a very high torque and gets spinning so fast that it can actually spin fast enough to damage the motor before you get enough back EMF to slow things down. So you probably won't run across that with drill motors or appliance motors, but if you have the motor out of its appliance or drill and you run it by itself, make sure you have some load on it because you don't want that motor breaking. It could actually fly apart and cause damage, especially if you have it apart. Like I said, you could have parts flying around. It could be dangerous. So be careful about starting a series electromagnetic motor without any kind of a load. Now, of course, we can also wind the motors in parallel, or a shunt wound motor as we show here. And the difference is that the current going through the field windings does not go through the armature. And so the current through the field windings is constant and is not affected by the turning of the armature. So in the series wound motor, the armature slows down. We get more current through both the armature and the field coils. But with the shunt wound motor, we do not get increased current through the field coils. And the consequence of this is that the motor is somewhat self-regulating in its speed. As it starts to slow down, we get less back EMF, so we get more current through the armature, and it tends to speed up. And if it gets less load and starts to speed up, we get more back EMF and therefore less current, and so it tends to slow down. Now, they're designed in such a way to optimize this. The number of turns of wire in the field coils compared to the armature are different. There are more turns in the field coil than in the armature, and the way they're made is to make this self-regulation optimized. But basically, your shunt wound motors are self-regulating in speed, and you don't have to worry about starting them without a load because they don't have a lot of starting torque, so they won't speed up too fast when they start, and they will tend to self-regulate. Now, once again, I am showing armatures with only 2 poles here. Those are not really practical. It's just shown for demonstration purposes. We will tend to have 3 or more poles on the armature, and that would be an odd number of poles because if we have an even number of poles, we can still get that situation where it won't want to start. And so you'll find your small motors tend to have 3 poles or 5 poles or 7, and as the motors get bigger, we get more and more poles in the motor. Once again, here's a universal motor, so this would be a series wound electromagnetic motor. So you see the windings for the field coils and the windings in the armature, and we see there are many poles in this one because it's a bigger motor, and so the more poles we have, the more efficiency we have, because the poles that are not in the magnetic field aren't doing anything. So let's only put power to the poles of the armature that are in the magnetic field, and so bigger and bigger we end up getting more and more poles, and then we have the brushes connecting to the commutator you can see here doing the work that we showed, but just more poles than the 2 or 3 we've been showing. And now, talking about DC motors in general, you might get the question, what about brushless DC motors? So these motors use brushes to make contacts with the commutator. What about brushless DC motors? Well, those are beyond where we are in the course right now, mainly because brushless DC motors aren't really DC motors at all. They are run by DC, but that DC goes to electronics that actually control the motor. Here's a good picture of a brushless DC motor, and we see a number of coils that are stationary. So in the brushed DC motor, we have the stationary permanent magnets, and then the coil moves inside the magnets. In a brushless motor, we have stationary coils, and the magnet moves around the coils. So this one here, we have a number of coils, and we use electronics to switch which coils are energized so we can rotate that magnetic field. And then the overturned cup here has a magnet around the edge, and we turn that over and put it over these coils, and as those coils get energized, rotating the magnetic field around, the magnet in this cup chases that magnetic field and causes rotation. So you see, it's not related to a real DC motor in any way. I wouldn't call it an AC motor. It's a motor all its own, but it's electronic, not mechanical like these motors we just talked about. And once again, it's beyond where we are in the course. Just another quick look here. Here's another brushless DC motor that has two coils in the stator, and there are 6 permanent magnets in the fan blade part of it, and that flips over onto the other assembly, and these 2 coils are energized alternately, creating magnetic fields for those 6 magnets to chase around and cause the rotation. So a completely different concept, probably not so difficult to follow, but that's what a brushless DC motor looks like. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocademy.net, you can go to patreon.com/join/vocademy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.